things, and you build those smaller things out of even smaller things. And when you're a programmer, you get to understand quite frequently that those smaller things are not necessarily simpler, right? We're programmed from physics to think that smaller means simpler, but at least in computing, that turns out not to be true, right? So you can build programs that are made out of programs that are just as complicated as the program you made them out of, right? That's typically called recursion. And nature does this too, right? So nature has superorganisms like beehives that behave as if they were a single organism, right? And interestingly, they're made of organisms, right? And even more interestingly, those organisms are made of cells, which are remarkably autonomous and organism-like, right? So this is a trick that nature likes to use. And if we think about scaling, and we think about how this works out in terms of nature or financial networks, what we'd like to be able to do is to have networks made out of networks, just like we'd like to have contracts made out of contracts, right? And we'd like them to be able to behave and execute with a high degree of autonomy, okay? So human engineers understand this already, right? So the internet is made out of lots of autonomous devices. And, you know, those autonomous devices, like, like this one here, are running lots, typically, or can do, lots of concurrent autonomous programs. And the programs are made of subprograms, et cetera, right? So these are principles that we utilize every day to scale. And it was as if we suddenly had amnesia when we got to the blockchain, right? Okay, all right, so I've belabored the point. So the thesis is that in order to build a scalable, public, economic, censorship-resistant blockchain, we need to begin with a conscious choice, a deliberate choice about the model of computation that we utilize, right? So let's take a step back in history, right? So the Satoshi, whoever she or he or they were, builds essentially what is a replication technology, right? We can take a state and with no centralized authority, we can replicate it out safely, right? And the first thing that Satoshi, the first kind of state that Satoshi replicates is what? Effectively a kind of ledger. We can simplify the blockchain in that way, right? And the Ethereum innovation as well, instead of replicating the state of the ledger, why don't we replicate the state of a virtual machine, right? It's a groovy idea, right? But at 20,000 feet, it's a groovy idea. And when you start to try to scale that, a lot of things fall away, right? So the first thing that we need to do is to focus clearly and carefully on the kind of computation that we want to execute with that virtual machine so that it's targeted at the domain that we're interested in, right? So if we were interested in building programmatic financial instruments, then we need to be able to do all the things we just talked about, right? So build financial instruments out of financial instruments, identify when financial instruments are dealing with transactions that are isolated, right? And run those in parallel, fine-grained parallelism. So let me state those intuitions in slightly more precise language. Okay, so first of all, the Ethereum innovation idea thought was, hey, why don't we make arbitrary programs, arbitrary computations be our notion of contract? Yes, that's an obvious one. That's a good one. Cool. So we call that completeness. So after Turing complete. Also functionally complete. It's an alternative phrase. Another one is compositionality. So computations, contracts, and even blockchains themselves should be made of computations, contracts, blockchains, respectively. Okay, so that turns out to be important. That's not how Ethereum is built. And that's what they're desperately trying to get to in the next round of innovations, right? And sharding is not that either, right? Sharding is just two-level, right? When I say compositional, It's in-level sharding, indefinite level sharding. Okay, so that's a different idea, and yet it's something that we recognize is what nature does all the time. So we ought to be able to just pick up the idea and run with it. The other point is that concurrency needs to be fine-grained. So the computations and the contracts need to be able to run with fine-grained concurrency. This is not what happens here, as anyone who's programmed the EVM understands. Okay? Now, anyone who's doing this should be going, but wait, how do you guarantee determinism? How do you make sure that you don't run afoul of, when you have non-deterministic order of transactions, what's going to happen, right? How do I prevent double spend and a bunch of things? We want to talk about exactly that over the course of this talk, right? But concurrency needs to be there in order to scale. Okay, and then finally, the other point that was very clear, that was very nice with respect to Ethereum, was that you need a notion of complexity. Why? You want to be able to count the usage of basic resources, space and time. And the reason you want to do that is because if you make a public machine, right? So what we're talking about is a public global computer. That's what you build when you put a virtual machine on top of the blockchain, right? So it's a public global computer, and so obviously it can be DOS. So what you do is you prevent the DOS attack by making people charge to run the computer. How are you gonna charge? Well, you charge by saying, well, you pay for space and you pay for time, where time is the number of steps in the computation. So 4 C's, just to repeat, right? Completeness, compositionality, concurrency, and complexity, right? Right. And it turns out that there's a little bit more. There's a little bit more to this, but just to be clear, right? With respect to Ethereum, they have the top and the bottom ideas, but they missed those two. And now they're desperately trying to wind back and go get a model that matches that, right? As opposed to beginning from the ground with things with a model that already had that, right? So this is already an argument for beginning with an appropriate model of computation that matches the domain requirements. Is that making sense? Are people kind of following along? Sweet, okay. So there's some other things that I argue are also important. So when you choose your model of computation, you want the model, the choice of your model, to allow for correct by construction implementation, which means that the model itself is clear and precise and formally verified, and that every step from the model to implementation is effectively auto-derived. There's no other way to do it at a certain level of detail, in which case you have very, very few proof obligations. So let's consider the alternative, okay? The alternative is you have the EVM, which was pulled out of someone's head. And you have Solidity, which was also pulled out of someone's head. And then you wire up a compiler from one to the other. And the relationship is effectively arbitrary, right? And now you have a proof obligation. The proof obligation is you must show that the compiler produces the bytecodes that line up with the semantics of the programs in the original source language. So let's see where we are with respect to Ethereum. Does Solidity have an independently verifiable semantics for the source language? No. Okay? So that's a problem because we don't even know what the programs in the source language are actually supposed to do. Okay? But let's say that comes along, right? That should be supplyable. All right? So that comes along. We take it as stipulated that some bright graduate student is going to provide an operational semantics for Solidity. Cool. So we've got one. Right. Then we have the operational semantics of the EVM, which was nicely characterized in Gavin's yellow paper. Right. Now we have to prove that when you take the source language and you compile it to the bytecodes of the EVM, that the bytecodes you get match the original operational semantics of Solidity, right? That's a proof obligation. And if you don't prove it, what's the problem? Anyone have any idea what the problem is? It's already shown up in the wild.
Bugs.
Well, not just bugs, actually bytecode injection attacks. This is a security issue. You can now, if we don't know what the bytecodes are supposed to do, then anything can interject itself and add a few bytecodes. I don't know, is that correct? Not correct, I don't know, right? But hey, these bytecodes just happen to drain $50 million out of some account. So that's an important feature, right? That's why correct by construction is important for this particular domain. Okay, so in general, you go from there to the formally verified proofs of the correctness of the implementation. So what I mean is you automate the proofs for all the pieces where you actually had to produce a proof. Okay, so I mean, so like in actual theorem provers and model checkers, like like Koch and Agda, and the spatial object model checker and things like that, right? So that gives you an important ingredient that is sociological in nature. If you think about it, right, the whole point of the blockchain was to reduce the amount of institutional trust that was necessary in order to run these applications. Okay, and then what happened? Well, all the expertise, at least with the Bitcoin blockchain, got located into Bitcoin core dev. And now we all have to trust Bitcoin core dev. Hey, does it work right? I don't know. Blue Mad says it works right. Right? Is that any more trustless? No, it isn't. But if you have these formally verified proofs, right? Anyone skilled in the art can go use a machine to check that the code does what it says it was supposed to. Okay? So Ethereum is nowhere close to that, and I just pointed that out in the number of different. Again, I want to be clear. I'm going to make a lot of distinctions between RChain and Ethereum. I am a huge fan of Ethereum. I'm a huge fan of everything that they've done. I think this kind of bold and aggressive push is something that's necessary. It's going to entail a lot of risk. But if we don't take those kinds of risks, then the kind of change that we need to see happening won't happen, right? And I have a lot of gratitude to be able to come by with a taillights view of the trail that they're blazing. Right? So this is in no way, ours is better than theirs. It's really just observing how we can all improve each other's work. So another piece of the formal verification is, sorry, I picked up a flu and it just
water on the desk.
Oh, thank you. Okay. So the other part is, hey, we're building contracts like the DAO, which could potentially be moving hundreds of millions, if not trillions of dollars, right? So we'd like to know that those contracts work instead of having a fatal flaw which would allow an attacker to drain $50 million out of it. So, and we want to be able to add those formal methods into the development paradigm in a way that is normal and natural. Right? If you say, oh yeah, you have to learn this other technology and you have to work with these other gurus and propeller heads, right? And that's a no-fly kind of solution, right? It's got to somehow fit inside the methodology. All right, and then finally, this is such an obvious point, right? It's something that the industry has known now for decades, I mean, literally decades, which is that programmers don't write programs. Programs write programs, right? Even if you're using a text editor, right? You're amplifying your own productivity with a program to help you write programs. And this is at scale, this is much, much bigger, right? So you have to have an honest to God meta programming capability. And this is why most of the major languages have ultimately, think about it, back in the 80s when the wild-eyed and crazy-haired Lisp programmers were like, program is data, data is program. What were they talking about? They were talking about the fact that because you could use Lisp to program and make Lisp programs, right? You had this enormous, giant lever in terms of productivity. Unfortunately, Lisp was too slow and couldn't beat out C++. But when Java comes along, what's the first thing they do? Right? They add in reflection to exactly support this kind of meta programming capability. What do you find in C#? Reflection. And in fact, it's quite interesting because all of the research languages are now moving into this direction, right? But so even Haskell has template Haskell, OCaml has meta OCaml, right? This is a fact of programming. So meta programming is an important feature if we want this to actually be in industrial scale. Right. So these are the things that I argue must be a part of your core notion of computation. So let me place this in context. Essentially, when we're talking about a node of the kind that we're suggesting, where you have a blockchain that's storing VM state, what you're really storing is a chain of blocks that are deltas on the VM state, right? And there are a few other things, a few other pieces of the node that are sort of big architectural chunks. One is the consensus protocol that's used to coordinate amongst the nodes, right? So in the case of the Bitcoin blockchain, that's proof of work. In the case of RChain, it's a variant of proof of stake that comes from the Casper family of algorithms. In addition, you have a local store, and you also have a comms layer. And if you put your architecture hat on, right, you spin the propeller and you look at this thing and you say, most of these components are all independent, it turns out that's false. When you dive down into the details, the model of computation that's encoded in the thing that you're storing as deltas on the VM state touches everything. In particular, as just one example, right, if you're building real applications, addressing and updating content, like say in a social network, right? Yeah, that would be a nice application to have as a decentralized application, right? So addressing and updating content turns out to be one of the biggest factors in the performance of your application, and the model of computation is determining that element, right? So that gives you a sense of how important that choice is. Okay. So, hey, let's just be engineers, let's be computer scientists, let's not leave this to chance, right? Let's just go survey the models of computation out there and say, hey, which one should we pick, right? Right? And on the basis of what? On the basis of the criteria in the domain that we just argued, okay? So we just argued that we need completeness, we need compositionality, we need concurrency, and we need complexity. Those are the 4 C's across the top. I have argued for metaprogramming. That was my last point in the previous slide. And I also argued for formal verification. That shows up as a kind of type theory. That's what that column is. And I'll show you how types fit into formal verification in a bit. Now we can just walk through them, right? Turing machines, are they complete? Yeah, that was kind of their big claim to fame, right? Are they compositional? In other words, can you, inside the model of Turing machines, as a part of the theory of Turing machines, can you take 2 Turing machines, whack them together, and get a third? Are they concurrent? Okay. Complexity, yes, yes, actually. And this is why if you go do a survey of the complexity literature, right, up until Girard discovers linear logic, you find that most of the complexity results are expressed in terms of Turing machines. Type theory, metaprogramming. So this is a terrible model if we were going to reason about computations designed for the blockchain. Lambda calculus. Why is lambda calculus important? Because it sits in the center of every single functional language on the planet. You are a functional language if the core model of your computation is the lambda calculus. So let's talk about that. That's OCaml, SML, Haskell, Clojure, Scheme.
Scala.
What's that?
Scala.
Scala, right? So just a few minor languages. Okay, they're all functional because at their core is the lambda calculus. So let's see if that actually fits as a language for programming the blockchain. Is it a reasonable model of computation for programming the blockchain? Completeness, yeah, all right. We're off to a good start. Compositionality, ooh, that's an improvement. Yes, you can take 2 lambda terms, whack them together, and get a third. That's kind of the whole point of the lambda calculus. Awesome. Concurrency, nope. Berry's theorem tells us that the lambda calculus is a model of sequential computation. Okay. Complexity, nope. There was an old joke back in the 80s. A Lisp programmer knows the value of everything and the cost of nothing. And that's because the core computational rule of the lambda calculus data reduction copies resources willy-nilly. And so until there was Girard's linear logic, which gave us linear lambda calculus, it was terrible for complexity, which is why up until 1987, we saw hardly any complexity theory carried out using the lambda calculus. Okay, type theory, yes, it's really good at that. And the simply type lambda calculus spurred a whole bunch of computer science that I'm not going to go into because we don't have time. Metaprogramming, kind of, sort of, but not in the way that I mean here. So, no. Petri nets, that's a great model of concurrency. It's complete, but no, it's not compositional. You can't. It took decades and decades and decades for people to come up with even semi-credible proposals for how to take two Petri nets and whack them together to get a theory. Okay, type theory, no. Metaprogramming, no. Okay, so that sucks. CSP, CCS, we don't get to most checks across until we get to the mobile process calculator. I put the Pi calculus up here because it was the first. There are a bunch of others. These are calculi that were intended by their inventors to be like the lambda calculus, but for the domain of concurrency. Right? So if you go read Robin Milner's Turing Award lecture,
I almost got page 1.
What he says is, I wanted something that was to concurrency as lambda calculus is to sequential computing. Okay, and so it meets almost all of the characteristics except for the metaprogramming. And the row calculus, which was something I discovered in 2004 and published in 2005, is the only model of computation that has all of these criteria. And again, this is all objective. This you can any mathematician, any engineer can go and verify each of these properties. So I argue that that's the model we should be using to program the blockchain. But before we make that argument, I just want to point out how this actually works. Right? So let's say we're going to design the VM surface language and the compiler pipeline from, I write contracts here to I run contracts here, right? So how is that done in industry? So if you are interested in correct by construction, this is the way it's done. You begin with a domain calculus, like the lambda calculus, for example. And you auto-derive by enriching it with features the surface language. It's kind of hard to do arithmetic with the pure lambda calculus. This is tedious. I mean, it's fun if you're a weirdo like myself, but otherwise it's not going to get your job done, in any timely fashion. So you enrich it with features and you produce a programming language such that you know that if you boil away all the features by compilation, you get back to your core calculus, and that process is just a reversal of the enrichment process, and so you know it's correct by construction. Likewise, there is a set of standard procedures now for going from the core calculus down to the VM. Right? So Oliver Danby and co. have figured out how to auto-derive the abstract machine, and then from the abstract machine to a particular VM is also auto-derivable. So if you have the core calculus, you can auto-derive the correct by construction surface language where humans talk to endpoint where machines talk. That's how this is done, and you don't have to take my word for it. Go check for yourself. I worked at Microsoft, and I spent some time with Simon Peyton-Jones, so the guy who invented Haskell. So I know Simon, right? And Simon frequently pointed out to me that for Haskell, System F was, in fact, the core computational calculus. It's a variant of the lambda calculus, which has a very rich type theory, right? He was interested in building that, right? And so that's how the surface language Haskell was derived, and how the spineless tagless G machine, which is the machine that makes Haskell scream, right, was also derived. Right now, there was a lot of work over the intervening decades, so it's hard to see this pipeline as cleanly and as clearly as in more modern languages, because people have been tinkering with it and pounding on it. But you can still see the vestiges of this pipeline if you go look at the Haskell code base right now. Okay, Scala is much, much clearer, right? And in fact, they've recently done a refactor because of the lack of soundness of their type system, right? It's been hard for them to prove certain soundness properties of the type system, so they went back to the drawing board and they derived the dot calculus, and now they have a surface language, which is Scala, which effectively fits the dot calculus, and then they have a nice, clean compilation path, and they are building all of the formal verification kinds of tools and proofs that are necessary on the basis of this re-implementation. Go check out Dotty, right? So this will give some credence to the claims I'm making. Now, so what I'm arguing is we replicate this for the blockchain. Hey, if it works for Odersky and Simon Peyton Jones, we could do worse than copy them, right? So this is the proposal that's on the table. We begin with the calculus that fits the domain, right? So, I mean, again, this is really just common sense. We start with an analysis of the domain. We say what's necessary, and then we find a calculus that fits the domain, and then we follow best practices. What is a reasonable service language? What is a reasonable VM? So it turns out that if you want to enrich the row calculus to a surface language that makes contact with the way programmers are programming today, well, one of the biggest, most important discoveries of the last, I think Eric has been thinking about this since 2005. So what's that, 11 years? So Eric Meyer, who was working on Link inside Microsoft, right, and a bunch of other people noticed, hey, if I generalize or make polymorphic the select from where pattern, I can cover virtually every major case from big data to complex event processing, right? So the for comprehension, the monadic structuring of code is you will find that is quite prominent in the row line that we derive from the row calculus, and I'll show that in a few minutes. So we've talked about all of that. So now I'm going to give you a big scary model. This is the model of computation. It's really, really, really big and scary, isn't it? Right? Pages and pages of theory. No, the point of these things is that they boil down to essence, the core of the computation. Just like the lambda calculus. You can write down the lambda calculus in about 3 or 4 lines, right? Same thing here, right? It's teeny tiny. Why? Because it's like Go. The rules are simple, the play is complex, right? And we need it that way so we can reason out about our programs. So let me just walk you through what this says, right? How many people here are familiar with B and F? 1, 2, 3, 4. Cool. All right. So B and F is a way of describing grammars. It's a way of describing syntax. But the way it's used in modern computer science is a way of describing abstract syntax. So this is not necessarily, for generating parsers. It's literally for describing data structures. So the top line really describes the set of data structures that support computation. In other words, you can think of it as describing the state of a virtual machine. The middle lines, and I'll go through it in a minute, just let me give you the overview. The middle lines describe for us some equivalences that hold over state. Okay, so there are going to be some things. How do I describe this? There are going to be some things in the state which, when we represent as data structures, the data structure is giving us too much structure. Right? There are distinctions in the structure that aren't meaningful in terms of the state of the machine, and so we want to erase those distinctions. Right? And that's what the middle line is doing. It's providing a kind of equivalence across certain data structures. We'll talk about that in terms of more common sense. And then finally, we have some transition rules for the virtual machine. That's all there is to it. You have a state, you take it to a new state. That's it. That's all that's on this page. So let's talk about the state of a virtual machine. Now, there's one thing that's different about certain kinds of language designs that doesn't often get talked about when we talk about computer science as application to the real world. So we can analyze this in terms of a pure functional language versus something like Java. When you have a Java program in front of you, you don't have the whole picture because the VM also has a stack and it's got some registers. And so when you're looking at this program, you have to keep over, as a programmer or developer, you have to keep over in the side of your mind somewhere a picture of these other, of the rest of the VM state, because that impacts how your program executes. Okay? By comparison, the lambda calculus has nothing else. You just have the program, and how the program evolves is determined entirely by the program and nothing else. Which means when you're looking at the program, there's no extra cognitive burden to reason about the program. Which has huge impact when you're talking about what? Formal verification of programs and contracts. Okay, so the same thing is true here. What's going on here is that we have, you could think of it as, let's see, 1, 2, 3, 4, 5 different constructors for programs. What are the 5 constructors? So we say that a program, say P or Q, so we're letting P and Q range over programs. I also call them processes. And that's because they can execute concurrently. So a program is either the program that is doing nothing, it does nothing, it's stopped, it's terminated. That's the 0. And then that first vertical bar is a choice. It could be either this or this thing, the thing on the left or the thing on the right. So the thing on the right is a for comprehension, right? So if you're familiar with programming in Scala or other kinds of languages like XQuery or other things like that, the for comprehension is a generalized select from where. And the way you read it is, from X, we're going to receive Y, and then we run P in an environment where Y is substituted with whatever value we got for Y off of X. Right? So you can think of this as an I/O blocked process. Right? Sitting there waiting on X, I'm just hanging out, right? Looking at this queue, and whenever a message comes off the queue, right, then I've got my value for Y, and I can go on and run P. Okay? So that's input guarded process. Likewise, we have an output guarded, or an output process. This is an asynchronous version of the calculus, meaning that there is no continuation after the output. Right? So we just fire and forget. We send messages. What kinds of messages do we send? We actually send the codes of processes. So it's like sending JavaScript across to the browser, right? That's the idea, except now it's a part of our formal structure. Okay, cool. So we can listen on channels named by X, and we can send on channels named by X. We can also take 2 processes and run them in parallel. So that's the vertical bar between P and Q. So just to be super clear, so what I said was the stopped process, the input guarded process, this one, the output process, asynchronous output, parallel composition of processes, and here's one that's kind of new and interesting and distinct from the pi calculus, which is that if you send me some code, I ought to be able to run it. So X represents a kind of code. And so now I start turning it in, I turn it from the code into the running process. So that's how we get recursion in this calculus or in this model of computation. And then it turns out that we start with the idea that all channels are actually, this is the brain twist, all channels are codes of processes. So that's a really interesting little mind twist. It takes a while sometimes for people to get their heads around. Okay, so if you're comfortable, then the next level is all just common sense. If you run P in parallel with the stop process, what's it going to be? Well, it's just P, right? If you run P in parallel with Q, right? That's this one here. If you run P in parallel with Q, well, gosh, that's pretty much the same as running Q in parallel with P, right? It's just a syntactic accident that we wrote one down. Right? And then likewise, if you run P in parallel with Q running in parallel with R, well, it's the same as if you run P in parallel with Q and run that in parallel with R. These are all common sense. Nothing major here. And then the final line here is also very, very common sense for any programmer, right? If you're a programmer, then you know that if you have a program that is parametric in some argument, say y, then everywhere in the body of the code you change y for z, it's the same program. Yeah. I have a C function, right? And everywhere, and the C has a parameter y. If I change that y to z, and everywhere in the body of my C function I change the y into a z, then it's the same program. So that's what this line here says. Okay, and now the remaining transition rules of the virtual machine are also dirt simple. The whole point here is how simple this is, right? The remaining transitions are, hey, if I'm running an input block process that's waiting for input at X in parallel with something that's sending at X, what happens? The data that I'm sending on X hops over to the thing that was waiting for X and is available in the continuation of the thing that was waiting for X. So that's what this line says. Let me walk through that again. So here's the thing that's waiting for data at X. Here's the thing that's sending data on X. What is the data? Well, it's the code of Q. So when the communication happens, they synchronize at X, and Q, the code of Q, is bound for Y in the body of P. That's what this little phrase here means. And that's it. That is the major computational rule, and it's as simple as the rule as beta reduction in the lambda calculus. And these other rules are basically just saying, hey, look, if P can make progress on its own, then when you put it in parallel with Q, it can still make progress on its own. That's this rule. This one says that these rules for erasing differences, they apply for the whole virtual machine. So it says that if P is structurally the same somehow as P prime, and P prime goes to Q prime, and Q prime is somehow structurally the same as Q, then P goes to Q. That's it. That's the whole model of computation. Now, let's put that in action. Let's see, let's see if I can, this might, oh, whoops. There we go. I don't know if this is large enough for you guys to read. I can probably do this.
Domain on your email.
No. That's really weird.
Enterprise might be a problem.
Oh, thank you. Yeah, that's terrible. There we go. Okay, and now let's go to so you guys can all go check this out yourself. Let's go here. I'm in the midst of doing a source-to-source translation. So here are some examples. And let's go with sugar. And let's take a look at this one. No, not that one. Let's try this one. Yeah, there we go. And let's see. Oh, that's better. Okay. So what this says, and then all we've done is add a little bit of syntactic sugar to the model I just showed you. Okay, what this says is I have a contract, and it's going to model a basic cell. How does the cell work? Well, it takes 3 channels. One is a channel where you're going to request to get the value that's being stored at the cell. The other is a channel where you're going to request to set the value that's in the cell. And the third is the channel where you're actually going to store the value. It's not the value, it's the channel where you're going to keep the value. Okay? So that's actually important. Channels act like pointers. They act like global internet scale pointers. Cool. All right. And so what happens is we run a choice, right? And the choice, so, which is represented by the keyword select, and the choice says, hey, there are two possible cases. Either I get a message off of the get channel, and that message contains a return channel, a channel to send the value back on. And at the same time, I go grab the value off of the state. Right? So this is a pattern of communication. I sit here waiting. I'm waiting on two channels simultaneously. One channel gives me the value of the state. The other channel gives me a return channel to send back the value of the state. In that case, what do? Well, I send the value on the return channel in parallel with putting the value back on the state channel because I took it off. Right? I'm not updating anything. I just want to put it back. And then I want to recurse, running the cell again so it can do what? It can continue to serve requests. So this is a persistent contract, and you could see how you could write terminating contracts, right? If I didn't recurse, this would stop after the first request. Okay? Now, the other possibility is on the set channel, we get a new value that we're going to put over in the state channel. Likewise, we go and grab the value off the state channel, and then we put the new value on the state channel, and we recurse, right? That is the entire cell contract. Out of this, you could build a wallet if you wanted to. And in fact, what we'll be releasing very soon is a tutorial on how you beef this up to build a wallet. It's teeny tiny, and you can see that already we're using concurrency inside a single contract. Okay, so that's Rolang in one easy lesson. Here's a wider view of the language. This is almost the entire surface of the language, minus a few little syntactic gewgaws. You can read about the language spec. It's up and available on the Rolang sites, on the RChain sites. So you can read about this. But again, the point here is how tiny the language is, and yet how expressive it is. To give you another example of how expressive the language is, one of the interesting facts about JSON is the way it embeds in JavaScript, right? So a JSON representation is a well-formed Java expression, JavaScript expression. So could we have the same kind of data representation in Rolang? It turns out we can, right? So I'm just reminding you of the sort of core of the Rolang language here, and over here is the core of JSON. And you get a one-line translation of JSON objects into the Rolang core. Right? So we have we now have our own data representation language, which we call RChain. And this allows us, yeah. You know, you gotta like the blockchain up somehow. The point is that this gives us a means to both go to store and go to the wire in a mechanism that is syntactically valid inside the language. And if you were to execute the translation, it would actually store the value. Right? It would actually store, remember I showed you that picture of the node? Right? It would store the values in the key value store in the right way. So there's basically there's no other programming model that you could hand me that has this level of fidelity. right? But it goes further. Let's take a look at the semantics a little further. So if you look at the four comprehensions, what they really represent are transactional boundaries. They're about transactions, right? The P that's waiting for the value, that continuation, that rest of the program gets to run only after state has shown up in the addresses, right? So when you update, so if you think of the X's where you're waiting as addresses on the blockchain, right? What you're saying is when these values show up at these addresses, then I get to run P, and not until that case, right? So this represents the transactional boundary so faithfully that we have, in the same way we have RChain as a data representation of JSON, we have a programmatic representation of blockchain structure that's one for one. So if you think about what I just said, here's a block. Forget the header for now. There are a bunch of transactions. Each of these transactions correspond to updating addresses with particular values. Okay? And what we're saying is that the program that runs after this has got to see that these transactions have committed, right? So that's exactly how we write it down in Erlang, right? The for comprehension gives exactly those transactions, and then here's the remainder of the program, and again, it recurses. If this is a for comprehension, this is the next set of blocks. So the blockchain is literally nested for comprehensions. So this is the point of picking a model of computation that matches the domain. What time is it? I can take a break here. 7:23. Okay. What time do we begin? You know, I could go on all night. What I wanted to show you perhaps was the virtual machine that we target from Erlang. But why don't I take a break here and open it up either for Ed or Joseph or for questions. I mean, like I've been going on and on and on, and I usually get feedback peppered all throughout the talk, so I'm not used to this particular style. What say we?
Well, yeah, it's a good for a break. I'm going to just move close to your microphone for a second.
Yeah, I'll just give it to you.
Okay. Yeah, we have, Michelle, how late do we have the room? Until 8, yeah, so, sorry? Okay.
Oh, thanks.
Yeah, Greg, this is awesome. And I'm, I've been working with Greg for about 2 years now, and I'm so inspired with him and every interaction we have. I got started in Bitcoin and blockchain because of the technology, and then my worldview expanded to include all the social ramifications and financial ramifications of blockchain. And so I just wanted to elaborate a little bit on the organizational objectives and also our motivation for this meeting. So just to repeat some of what Greg was saying at the beginning, we have a couple of organizations. There's the RChain Cooperative, which is modeled after REI, and it's a membership-driven organization where the benefits that are, the profits that are realized by the co-op will be distributed to its membership. We haven't had our membership drive yet. We've only been organized for about a month now. Evan is a director. Evan Jensen and myself and Greg are the initial directors. And the membership drive will be coming soon. And then, so that is going to produce open source software that's available to everyone. One of the primary purposes of it, in addition to funding open source software and organize it, is really to control the releases and control what's official RChain versus all the forks that may occur from RChain, which is great and innovative, but same thing with such such like the Ethereum Foundation, right? It'll say that's the official branch. This is how you can use the name Ethereum. And so that's, I think, one of the core functions in addition to that. And then lots of open source projects will be building dApps, and whether they be completely open source or whether they're connected to enterprises and so forth. And then the RChain holding company and LivelyGig are some of the for-profit entities that will work very closely with the cooperative on. And so my main focus over time is going to be on the holding company and LivelyGig and those for-profit entities. And Greg's focus over time is going to be on the cooperative more so, but we're going to collaborate as much as possible. And one of the, and I thank you all for coming, one of the this is informational, and we're also streaming, but we're also calling out for those of you online and for those of you present, if you want to get involved in the projects, please let us know. All kinds of ways that you can get involved, especially for developers who want to help build the platform. That's probably our most urgent set of needs. The website is http://rchain.coop as the primary site. And there you can join Slack and so forth. Greg, have you had enough of a break here, or ready to get back on?
Actually, so just quickly, why don't we, because Joseph has prepared a little bit more of a deep dive.
Good.
If you want to, so if people want, do people want to see sort of a more fleshed out contracts? Is that useful, interesting to folks? Okay.
Is that it?
Yes.
All right, very good. Cool.
Awesome.
Yeah, excellent.
Battery's dead? Oh, okay. And feel free to grab some cookies or additional drinks while we're shifting here.
Yeah, it's going to take me a little while to set up if everyone wants to stretch their legs for just a second.
You want me to close down, or you can still?
Yeah, that's a good idea. Sorry. Oh, you're good.
And I'll get off the wall socket so you can have that power if you need it.
Joseph, I'll let you know how much 10 minutes to go. Sure. Yeah. Right, 7:30. So like in 20 minutes? Yeah, sure. Shogo, are you on the Zoom room right now? Yeah, would you how's it look on your screen? That's what I'm saying.
Oh, I shut down the Zoom. You have to join.
I joined Christians.
Oh, okay, cool.
Yep.
Yeah, Joseph, we can hear you. Sounding good.
Cool.
Sounding good. Just place the laptop right near, where you're speaking at. Maybe try to I know you got to move around the room to make it a bit more expressive, but it's sounding good. Sounding good.
Can I see that?
Yeah, that's good enough.
Yeah, I think we're good. Could you repeat that, Alex?
Yeah, just try to place your laptop just right near where you're speaking, at that sweet spot. I know you're moving around the room a lot.
No, probably not. But
so just place it right in front of your face, as you're extending.
Yeah.
There you go.
You got it. I'll give it a couple more minutes. Anybody else we're waiting on aside from them? No? Cool. Hi, everyone. My name's Joe, Joseph Denman. I've been hanging around with the RChain crew for the past few months, since September, actually. And Greg would say the same thing to me that he's saying to all of you, which is like, wow, look how simple this is, right? Oh my gosh. Yeah, I'm like, oh, yeah, yes, really, crazy simple. Batteries are dead, supposedly. So, yeah, but it should be fine. So my job here, what we're going to do is a demonstration to kind of show the fine-grained programmatic concurrency that we've been discussing with the row calculus. So everything that we're seeing and that I'll show you in the demonstration, it takes advantage of the same internal structure that we assume on channels of concurrency, and is built directly from the Erlang spec. However, as a caveat, the demonstration that we're doing today, it doesn't compile. You can't run. It's a syntactic representation, but we're going to run it on the parser soon to see how it checks out.
Well, you should say that you've been developing it over in the last.
Yeah. I mean, we didn't just throw it together. Yeah. And you
should also mention your background.
That's right. Sorry. So I'm not a computer scientist. Actually, my background is in molecular biology or protein chemistry. That's what I graduated in. What I've just been doing here is taking advantage of the very accessible syntax and semantics given by the row calculus, which is what's so great about it, is that if you read the paper and you have and you kind of abide by the rules that are given you, pretty much anybody can pick it up if you have the core notions nailed down. So this is or I guess I'll start by saying, just kind of rephrasing Greg's words, concurrency, especially in RChain or in concurrency in general, actually, is the composition of independently operating processes, which essentially means that we try to make each process, each protocol, as self-contained as possible, right? So once we fragment different protocols, we need a way for them to communicate. Hence, the channels and names we've been hearing about since the beginning of the talk. So this is a larger contract for a load balancer. What you see behind you are essentially 4 smaller contracts, which all kind of compose to build a larger load balancer contract. You'll see the do work contract, which is all the way on the left, which generates a work request. This is essentially a requester, right? From the requester, the do work contract, we send it to a collector. The collector's job is to limit essentially the amount of requests that the dispatcher will ultimately take. Its job is also to do a little bit of pre and post processing to check for request accountability, to make sure that it's the result that we want, essentially. From the collector, our work request is sent to a dispatcher, and the dispatcher's job, as we can see here, is to spin off a worker, represented here as a contract worker behavior, for each work request that we get. And the amount of workers that we can generate, the amount of requests that we can take at one time, is directly correlated to the resources that, in this case, the node operator is bringing to the table. So we'll see that each worker takes a request and evaluates, and then sends the result directly back to do work contract, which is a requester, right? So you'll notice that just as a structural property that the workers don't have to communicate with the dispatcher or with the collector after they've received the work request and after they've evaluated it. They just send it directly back to, again, the requester. And after that, the last thing we'll see is that we're going to do some further processing with whatever result we get. But that's not demonstrated here. So without further ado, this is our requester. And it's important to notice also that this approach can not only be applied to a single node, right, to a single machine, but to a network. So we can take work requests on a single machine, right, and divvy that up between workers on a machine, or we could apply this same approach and take work requests from a number of different nodes and distribute them across the network to other nodes, which will then follow this protocol on those single machines. So we'll see that obviously, again, the larger contract or is load balancer contract, and it's parametric on a namespace, right? And so the idea has been, the thinking has been up until this point that each node will be responsible for listening on namespaces, and we'll hear more about namespaces in just a little while when Greg continues his talk. So the first thing we have to do, we'll see. Yeah, the first thing we have to do is define what a work request is. And a work request here is a structure of type fields, right? So we have an address and some sort of protocol or a process that we're going to want to evaluate. Our address is a channel, and our process is the quoted process, which, as we'll again see more of, is the code of a process, right? So that's all contained within our work request. Our do work contract, or the requester, is parametric on a number of channels. The node channel, KS, KF, and the gate channel are all channels that do work is using to communicate with other contracts. So the first thing we're going to do, and this is this is essentially a constructor, right? New return gate check in, right? That's syntax for construct these channels. Create a return channel where we're going to get our result, right? Create a gate check channel, and that is ultimately going to be where we send the result that we get back for further processing. And the in tagged onto the end is essentially just saying that these channels apply to the process that follows, or the body of the process that follows. So we're going to create a new work request with a return channel and some job in the form of a process. And we're going to send it on the node channel. And on the other end of this, as I'll show in just a second, is the collector listening on the node channel, right? So in parallel, and this is our first encounter with the 4 comprehensions Greg was expounding on earlier, wait for a result at the address or at the channel return, right? So again, the for comprehension is just kind of spinning, waiting for a result coming in. And once it gets a result, it's going to send that to the gate channel, right? In parallel, we are also waiting back from the gate check or from, our gate check, right? And when we get a result back, as we see here as check, we're going to match it, right? And we'll notice here that these are similar to the Scala pattern matching syntax because originally the language is going to be similar to Scala or even some of the structures that Scala uses. So when we get our check back or our message back, right, we're gonna pattern match it, right? And if we get something back that says true, then we're going to say our processing was a success. And if we get something back that says false, we're going to know that our result does not meet whatever requirements we have of our result. So this is essentially a requester.
So can I
Sure.
ask? So and again, this is Joseph's design. I haven't vetted this design all of it, making sure that the syntax is roughly compliant with this spec. But so I just want to ask you about the design.
Sure.
As I understand it, node, KS, KF, and gate are all channels.
Mm-hmm.
Node is where we're expecting to send the work to get executed.
Correct.
Right. So the node bang new work request.
Sure.
Now we're packaging up the work and sending it off to the node.
Yeah. Exactly. Yeah.
And then it looks like when you make a return channel that you stuff into the work request, and then you wait for the result on the return channel.
Correct.
Cool. So that's like a little conversation. Hey, go do this and let me know when you're done. Let me know.
Exactly. Yeah.
Right? And the next thing is the gate there's some kind of quality control character.
Exactly.
Sitting
Yeah.
on the other end of that gate channel.
Yeah.
So when you send a result and another return channel, which is the gate check channel, and then you wait on the gate check channel for the evaluation from the quality control character.
Correct. Yeah. I kind of blazed through that part.
No, I'm just checking to make sure I've understood.
Yeah. Exactly.
Sweet.
And then once we get that back from the gate check, we case it.
Sweet.
Yeah.
So then KS is some channel that's for success.
Exactly. Yeah.
And KF is for
Failure. Exactly. And so then as represented in the syntax we've seen so far tonight, we are packaging the result up and sending it on KS or bang, as we call it. So the next thing we're going to define is the collector. And the collector, we are communicating with the collector in the last contract through the node channel, right? So we'll see that the first thing we have to do is actually create a new work queue. And work queue is a channel, right? And it's going to apply to the rest of the body. This is a top-level declaration. And work queue is eventually where we're just going to send our work requests, right? The other contract listening on this is going to be the dispatcher, which we'll define later. So collector is parametric on node, the channel work queue we've just constructed, and it has an accumulator and a limit. So when we instantiate the accumulator, or we'll give it a limit, and we'll define these channels for it. So what we're going to do is wait on the node channel, which we were sending to in the past contract, for a message. And a message is a variable. A message is a pattern. It could be whatever we want it to be. But essentially, that something is coming in on the channel, right? And then what we're going to do is match it. Whatever we find on the channel, we're going to see what it is. In the case that it is a work request that has an address and a protocol, then we're going to actually match our limit next. So we're going to see, do we have room? Does the node still have available resources to process this work request? So in the case that our accumulator is less than our limit, we're going to send our work request to the work queue, which we define in the top level, and then we're going to recurse with our collector, and we're going to increment our accumulator. which is standard a standard accumulator implementation. In the case that our accumulator is greater than or equal to our limit, we're going to say no, we don't have enough room to process this right now. So we're going to return an out of memory message to the requester, and we are going to recurse our collector with the same accumulator and the same limit. So how do we decrement that? How do we lower our accumulator? Well, in the case that we get a quit message or a done message back from the worker, then we're going to recurse the collector with node channel, with the same word queue channel. We're going to decrement our accumulator because that means that our worker has either had to terminate the process or it's finished or completed the process. So the next thing that we have to define is what exactly our worker is. So we're going to create a new structure, a similar type collection of fields as we did before, worker struct, right? And we're going to define an ID that's an integer, a channel work that takes work requests, right? A worker queue channel, right? So the worker queue is in fact the channel that will hold the channels of the workers, right? So for a dispatcher, we're ultimately going to have a dispatcher that says, okay, these are the available channels that can receive work, right? And all those channels correspond to some worker that's created a channel for it, right? So ultimately, when we get when the dispatcher gets a request, and we'll see this in the next slide, we're going to pull a worker, right, off the worker queue and a work request off the work queue and match them together. We also, again, give the worker a quit channel. And quit channel is one that takes a Boolean, right? So it's just true or false, right? And depending on what comes in on the quit channel, we're just going to terminate. So again, this contract worker behavior, okay? It takes a node channel, or it's parametric on the node channel. It takes an ID, that's an integer, and a worker, right? And worker is a variable that will actually define when we instantiate them in the dispatcher contract that's up next, right? So there are a couple cases we have here. In the case that we have a work request on the work channel of a worker, then we're going to evaluate the process. So we'll see the, no, a pointer, but we'll see the asterisk process. Greg showed us that that's essentially the evaluation operator. We're going to evaluate the job that we were given in the work request. And then we're going to send the work request back to the requester's return address, right? So this is just like where the actual meat of it happens. It's when you get something, when you get a request, evaluate it and send it back to the person, right? But the important thing to notice here is that the worker doesn't actually have to communicate with the dispatcher or the collector. As soon as it's given, after it's given the work request, then they're free to operate independently and determine and return that result, right? So in the case that we do finish, right, then in parallel, what we're going to do is actually add our work channel back to the worker queue, right? So after we finish, we're going to say, all right, so I finished my job, and here's my channel so that I can take another request. And at the same time, we're going to tell the node that we're done so that we can decrement the accumulator, which would allow us to take, another work request. What's also interesting here is that one user, right, may issue, I don't know, however many work requests, right? But so long as they're up to the limit, right, say if the limit's 100, then we could theoretically witness 100 workers operating in parallel. And if you contrast this to, say, Solidity and the EVM, the equivalent approach would be that whenever we get a work request, that we would have to process each one of those, say it's 100 requests sequentially, which we could do, right, in this structure. We could do that. But the fact is, and the benefit is that we can just we can build up another worker for every work request so that we can process them concurrently and increase our throughput. So the other case is that we get that we get a quit message, right? And that it comes in, or we get a quit message on the quit channel of the worker. And when we do that, we essentially just have to tell the node, we're finished. we have gotten someone's told us that we have to stop, we have to terminate this job, and we have to tell the collector that we've stopped so that we can decrement the accumulator. And lastly, the dispatcher. The dispatcher is going to be essentially responsible for pulling worker channels off of the worker queue and pulling work requests off the work queue and pairing them together, right? So the first thing that we have to do when we're initializing when we're running the contract is we have to create a worker queue. And the worker queue is going to, we're going to create this channel that's going to apply to the body below it, right? So, so this contract then, or the next contract then, the dispatcher contract is going to be executed given n workers, right? We're going to specify how many workers we want to make, right? We're going to specify the name of a work queue where we're going to take requests, and we're going to specify the name of a worker queue where we're going to take worker channels, right? And so we'll see the first line under the first for comprehension then is we're essentially creating the amount of workers that we want to do. So if the number of workers that we have from 1 to n workers, if it's less than the number of workers that was specified, create a new work channel, a new quit channel, and give it to a new worker and build up a new worker.
Actually, that if there is not necessary because you're running it over the sequence 1 to n workers. So this one won't work like a
okay, gotcha.
A do while loop. You could just get rid of that. But these kinds of things are useful to talk about. You just need to run it from 1 to n workers.
Gotcha. Cool.
Yeah.
Cool. Appreciate it. So within the dispatcher contract, we're actually going to initialize the worker behavior contract. And so what we're going to do is we're going to give an ID, and every time that we run this, right, we're going to increment the ID that we give. So if we have 10, if we have, say, 10 workers, and we're going to go from 1 to 10, and each will have like a numerical ID that we'll do. And we'll also give it the worker struct as an argument so that we can create all the properties that we defined before for the workers. And after we do that, we'll notice here that we're just going to add the work channel to the worker queue so that it has something to receive work on, right? And the second for comprehension occurring in parallel, and this is like where the actual meat of the dispatcher occurs. We have 2 requirements. This one essentially says that when we observe a work request on the work queue, and we also observe a worker on a worker queue, that we're going to send the work request to the worker. Very simple. And in parallel, we're just going to recurse the dispatcher. So there have been other implementations of load balancers which exploit concurrency, but this one in particular demonstrates in a pretty fine-grained way exactly how transaction semantics fit into Erlang, right? So whenever essentially a value being stored at a channel or address or location, as we're calling it, right, changes, there's a formal model to account for that, and consensus to account for non-determinism. So for example, a transaction here could be shown, for example, when we send a done response on our node channel, right, we're essentially saying, send this guy, place this message at this channel, right? And when we do that, we also have the collector listening on the node channel for something. So whenever we see a message in the body of this next protocol, we're just going to substitute what we're sending, which is the done response, right, for the message, in which case we match, in the case quit match, and then we execute something else, which means that there is a, as Greg was saying earlier, a transactional boundary that's represented here. And essentially, anytime we send something and we place something on a channel, and then someone reads it from a channel, we want to be able to account for that. So I hope that I didn't blaze through that too fast, and that it at least demonstrated the particular, a choice implementation of the base syntax as it exists now. So thanks for listening. Appreciate it. Yeah.
Yeah, we're okay to 8:30, and it'd be great to hear a bit about Casper, Greg. And
Yeah.
other
absolutely.
Q&A comes up.
Yeah, actually, we've been talking at you for ages. I would love to hear back from you, and then we can go deeper on some of the other topics. But I think, if people, now that you've had a chance to see some of, this is actually only like about 30% of what goes into RChain. There's more. And then in fact, the other 2/3 just from a technical perspective. So we have a variant of that. And part of the variant, so Casper itself is like a big, huge thing, gigantic, a lot of interesting and rich computer science there, and how it touches on game theory and on distributed transactions and on other models of computation. That's all rich stuff to talk about. But our variation, which is different than the Alex version of our lab, utilizes another piece of work that we are working on that fits in how we ensure that the contracts are correct. So what Joe's discussion didn't present was the types for the contract. So essentially, most of his contracts were not type technical. We have a type system for the Roland contracts, which allows you to detect a very wide range of issues. So, for example, one of the things we did with the Dow bug, we rewrote the buggy contract with the bug inside in Roland. And then we just wrote down the natural type for that contract, understanding what it ought to be versus the issue, right? And it turns out that our type catches the bug. What that means is that the contract would never be deployed because it wouldn't be So that's a big difference, right? And it's not like the developers have to go off and learn this other formal method stuff. No, they write down the types for their programs, and then they have the compiler check that the programs are well typed, right? This is the way we know and love how to program, unless of course you're JavaScript. Sorry, I had to put that in. But where does this type system come from? And how does it fit with Casper? So where it comes from, really quickly, and I really want to hear from you guys, where it comes from is an algorithm that I've been working on since about 2007, and I enlisted Mike Stay to help me a few years back. Mike Stay is a brilliant mathematician, computer scientist, and mathematical physicist. The algorithm we call the Ladle algorithm. So it's logic as a distributed law. And it turns out that the algorithm works for any model of computation. So remember, I listed out all those models of computation at the beginning. So our algorithm says, if you give me a model of computation represented in a certain format, and you tell me how you want us to collect the results, then we can generate the type system for it. So what do I mean by collect the results? So what you want to be able to say is, does this program meet this type spec, right? And so you can think about that as a kind of filter, right? Collect me all the programs that meet this type spec. And so that collecting all the programs that meet this type spec, the collection methodology, you have to supply as an input. So you could collect them as a set, in which case you have no duplicates. You could collect them as a list, which would allow for duplicates. You could collect them as a tree, which would allow for other kinds of structure. So you give us as input the model of computation, how we're going to collect the results, and we hand you back a type system that includes the type checker, the model checker, and from this you can generate a query engine. Because if you think about a type checker or a model checker, it's a query language and a database engine turned on its side, which which means that this algorithm has all kinds of implications for searching for contracts. Right? So think about giant repositories of code. Does that ever happen in the world? I don't know. GitHub maybe, right? So imagine that the blockchain has the RChain blockchain has all these contracts. Why? Because RChain was successful, right? So now there are all these contracts. How do I go find the one I want? Right? Well, I find it using the type system. It actually becomes a search mechanism for finding the contracts. But the value for Casper is that it gets rid of the whole block size debate. And then here's the way it works. You, as we tried to say before, what you want is to allow for blocks that contain lots and lots of transactions that are all isolated from each other. You don't care about their order. Right? You don't care because they don't touch on each other. So imagine that you've got, instead of miners, you have a bunch of validators, right? And what these validators are doing is they're receiving transactions to potentially put in blocks. And they want to package them up in a certain way and then propose a particular block. And then what they're going to do is they're going to bet. They're going to bet on which block is going to make it next. And the betting behavior is subject to certain kinds of economic constraints, so that if they bet in weird or equivocating ways, then I should have said up front, Casper is a pay-to-play algorithm. So you have to put some value, some stake up front in order to play. And now, if you behave in weird ways, like in betting behavior, then your stake gets slashed. And so over time, the only validators that are left standing are the ones that have been playing nicely. Right? They're trying to converge to consensus on the next block and the next block and the next block as quickly and as efficiently as they can. Now, how do they describe what the transactions are in the block? So there are two ways in my slides. I was talking before. There are two ways to describe collections. Extensionally, so I tell you all the things that are in the collection, right? So A, B, C, right? That's a collection of the strings A, B, and C, characters A, B, C. Another way to describe collections is using rules and programs. Right? So here's a collection, all the even numbers. So I've just given you a rule, and then you can use this rule either to test to see whether a particular number is in the collection. So that's the filter method. Or to generate, you could write a program which lazily generates and gives you the next one and the next one and the next one. There's generators and recognizers, which are rule-based ways of describing collections. Okay, so it turns out that this ladle algorithm gives you a rule-based way for describing collections of things. In particular, to describe collections of transactions. How would you describe that? Well, how about transactions that are grouped by namespace? So all the transactions that are operating on this namespace are allowed to go now, right? And all the transactions that are between this time period and this time period are allowed to go now, right? So these rules give you a compressed way to describe big, giant chunks of transactions, right? I'm not worried about the size of the block. What I'm worried about is when we, as validators, all start to try to consent whether the rules you're proposing are consistent with the rules I'm proposing. So most of the time, like, let's say Shogo is a validator. He's validating the transactions from the Southeast Asian region, right? And I'm validating the transactions from the Pacific Northwest region, and they don't touch each other. And so, we could just combine his rules with my rules, and all of those transactions get to go, right? Which is awesome, because now we're talking serious throughput, right? But let's say that there is some, there's some transaction somewhere, I don't know, in Vancouver that touches, the Pacific Northwest and the Southeast Asian region. And my view of how this transaction fits in the order of transactions is different than show goes. Right? So now we have a conflict, right? And what do? Well, what the validators then do is they look, when they have conflicting sets of rules, they then look for the smallest consistent subset of rules. And there's a protocol for doing that. You calculate, not the smallest, the maximal. You're looking for the maximally consistent subset of rules, right? And that's when you use the Casper betting algorithm. So the Casper betting algorithm can be used for anything, but in this case, you're using it to bet on the maximally consistent set of rules, right? And once you have that, once everyone is converged on that, then you can unfold the transactions and boom, do the blockchain. This allows us to do tens of thousands, hundreds of thousands of transactions all at once. So that's how the ladle algorithm fits into the Casper model. So what do we talk about? We talked about the row calculus, row line model of computation as this giving us a virtual machine and a contracting language. We talked about the consensus algorithm, Casper, and then we talked about types and how these types allow us to make sure that we don't deploy bugs that we could have avoided, like the DAO bug. And we also can use it for searching for contracts on the basis of their structure and their behavior. Discovery mechanisms. So those are some of the major chunks of the tech that's going into RChain. So now that you've kind of seen, even we've opened the curtain a little bit more. Let me throw it over to you guys and say, are there any questions?
Okay, just to do a time set, we've got about 20 minutes and we need to go. Let's have some Q&A and then maybe 5 or 10 minutes of social. Yaman.
So let's say we're targeting for 50,000 transactions per second. What kind of security problems do you think there would be, or would there be any security problems with that?
Yeah, I mean, we have all the usual sets of security problems, right? So we have to be concerned with potentially malicious behavior of validators. We have to be concerned with cartels of validators. We have to be concerned with potential censorship of transactions, right? All of those hold here in this particular setup. And that's exactly why Casper turns out to be so nuanced and complex, right? But one of the nice things is that when you set it up in this formal, correct by construction way, a lot of the security problems you can analyze up front, right? And actually, there's a rich debate between Vlad and I want to do as much of the security up front as possible. So, for example, I can write down in the type system. Thank you, Sugar. I can write down in the type system types that guarantee that the contract. Think about it like this: it's like a compile time firewall, right? So I can write down a type such that if the contract satisfies the type, it will only ever engage on channels in this namespace, and will never ever, no matter what, engage on communications with channels in the forbidden namespace. So this is how you can put walls around things.
Sandbox.
Yeah, but it's a compile time sandbox.
That's right. That's cool.
Yeah.
Is there a block size limit, like 1K or some small content? Because otherwise it wouldn't be fast, right?
That's right. Any other questions?
Describe a little bit more about the namespace. I'm having a hard time understanding, like in the examples, what is the namespace?
Yeah, no, that's great. So remember how there was this funny little recursive line in the row calculus. And what it said was, well, processes are built out of names, but names are the codes of processes. So what's really going on is we're saying that names have internal structure. Now this is, I mean, if you're interested in computing and the history of computing, this is a rich debate. Robin and I went round on this, okay? Robin insisted that names in the pi calculus should have no internal structure. And I kept saying, no, it doesn't work that way. Like, there's no implementation on the planet that doesn't give names, channels, internal structure. If they're integers, they have internal structure. If they're strings, they have internal structure. He was worried that if you expose the internal structure, that people would then do pointer arithmetic on names. And what I was trying to say to him was, you can't stop that. So embrace it and then make it work for you. So let's talk about names that everyone's familiar with, naming schemes that everyone's familiar with that have internal structure. I don't know, how about URIs? Okay, so the real, when you go from the calculus, which is pure, the name structure derives purely from the process structure, to the Roe-Lang, where you have lots of different kinds of names, right? So names include process structure, but that's mostly just for the metaprogramming, right? When you're talking about organizing the computation at internet scale, names need to effectively be things like URIs. And then a namespace would be something like an X query, right? Which pokes a hole somewhere in the URI, right? Does that help? Cool.
Is this open source?
Yes.
So companies can just take the source code, they can buy a bunch of EC2 hosts, deploy it, and make their own currency, and then compute on it if they wanted to.
That's the idea. Yeah. As
how do you guys make money? How do you get paid?
So that's a good question. So first of all, we believe that this part of the infrastructure needs to be open source because all of the rich ecosystem of applications that would make money has to have this commons infrastructure. And if any one party owns that, then we're screwed. Okay? So remember, just like with Ethereum, the issue is you got to prevent denial of service. In order to prevent denial of service, you have to charge for all compute resources, right? So in order to make any transition in any one of these instances of the virtual machine, you have to have phlogiston, which is the RChain version of gas, okay? In order to get phlogiston, you had to buy it. So the only way to get that is through the token that is supported on the RChain network. So that's the RChain token. So if we're successful, the reality is the RChain cooperative is going to be making money hand over fist, but mostly what it will be doing is handing that back out to its membership. Okay? Mostly what membership gets you is rebates on your use of phlogiston, your use of the token. So you spend your $20 or whatever the membership fee is, and when you run compute, then just like in REI, at the end of the year, we hand you back a big pile of R token as a rebate against the R token that you used. Okay, so that's the model that is going to keep the RChain cooperative afloat without being too greedy, right? The reality is, if this is as successful as we believe it will be, the money that's coming in as a result of running computations on this is going to be quite huge, right? And then really what it has to do with is the network effect. Just like with Ethereum. I mean, anybody could go and clone Ethereum right now. How does Ethereum make money? And yet, amazingly, they are. How does that happen? It's because of the network effects. Because there's a ramp-up curve in order to come up to speed on making Ethereum work, right? And then it works better if all of the implementations work together as opposed to being separate forks, right? That turns out to be a better proposition for the community as a whole.
So like REI, that organization has a large overhead. They have to buy product, they have to have staff, they've got to build buildings. So your dividend or your rebate at the end of the year is it's somewhat small, right? Maybe 1% of your spend.
Yeah.
With the co-op, RChain cooperative, what's their overhead look?
Yeah, well, isn't that interesting, right? Because we don't necessarily have to pay for servers, right? Everybody's
Running their own.
running their own.
So you've got maybe
servers.
staffing,
You got
some
staffing,
legal,
yeah,
maybe some letterhead.
yeah,
Yeah.
accounting. It's a much smaller.
The possible rebate could be upwards of a lot. A
Yeah,
lot more than our
upwards of a lot. Yeah,
Yeah.
exactly.
I don't wanna say a lot more than you would expect for something like ours.
Yeah.
Because the overhead is lower.
That's the idea.
That's fantastic.
Well, we think it's a cool model, right? It has. I'm actually surprised that no one thought of using the cooperative model here before. It was Ed's idea.
Good job.
I don't think it's my idea completely.
We get to blame you anyway.
If there's
If it works, it was my
Then
idea.
it was your idea. Overland, right? But I think the other half of the how do you make money question is, I think of this a bit as, decentralized cloud computing, right? The cloud service providers make money, but that's sort of a different set of infrastructure than the applications that are running on the cloud, right? And so in the decentralized world, right, the cooperative and the node operators all over the world will have incentives and make money. But in addition, dApps and connected applications to enterprises, for example, will also have their own profit models or cost-saving models in the case of enterprises. If you look at the blockchain investment over the last, especially the last 2 or 3 years, it's been like $2 billion, or in that area. And some of that's going to startups, and some of that are like the banking system, investing in enterprise Ethereum projects that will save them money from, accounting and regulation and auditing costs, for example, right? So there's all kinds of profit incentives and cost-saving incentives around the whole ecosystem. So, pretty exciting. Greg left. Any other questions? He'll be back. Yeah. Yeah. So, yeah. Why don't we just break to social 10 minutes and say hi to those that you haven't met. And thank you so much for coming. And we'll post the video that we did capture and the slides on the RChain.coop Slack, which you can join with slack.rchain.coop is the URL to join, but you'll find that on the website. Any final comments or questions before we
I
break?
just thought of one.
Charles?
Any cool porting kits to go from Ethereum to RChain?
No, and there may not be such things, but there's maybe, like some simple contracts we can make functional, but in terms of general Solidity code, for example, it's not likely going to port. But, maybe for simple wallets or simple multi-sig kind of things, we could port them. But that's my understanding.
Should we ask Greg?
You can ask Greg.
All right.
What was the question?
So what if somebody wanted to port from the old faulty ways of Ethereum and Solidity to RChain, the new ways of business and scalability?
Yeah, I've been thinking a lot about that. Well, first of all, it's perfectly reasonable to imagine a compiler that goes from Solidity to the Rho VM.
All right, make it.
We're thinking of a more ambitious thing, and right now this is under hot debate within the community. So what we've been thinking about is a multi-token solution where it becomes possible to purchase phlogiston directly via Ether and directly via Bitcoin, as well as via the RChain token. So you have a multi-token chain. And right now, Vlad, for example, makes a compelling argument against what we've been calling this idea economic abstraction. He makes a compelling argument against economic abstraction, and Vitalik is sort of weakly agrees. But their arguments are general. Their arguments are, for a general set of tokens, this is hard. And my argument is, yes, I agree. For a general set of tokens, this is hard. I'm not talking about a general set of tokens. I'm talking about 3 well-established tokens. I'm not going to add any more. I'm going to limit it there because that gives me enough reach. And if you have a large enough reach like that, this is an advantage for everyone. So that's what's under debate right now. You know, Joe Lubin, for example, when I described the idea to him of Joe Lubin of Consensus, he was quite intrigued. He thought it had legs. But I really, you know, I want to run through all of the mathematical arguments to make sure it flies. So that's there's in the small, just compile solidity contracts that Rovium, that's cool. In the large, multi-token plus cross-compilation.
How do you solve the old contracts of again trying to bring
yeah, so I think that's actually kind of cool because then you catch bugs, right? Right? It's like when you compile it over and you try to type it, you know, the type system goes, did you really want to do that? You know?
Do you see an automated program that would actually do migration from the contract?
No. I mean, you can do cross compilation, but you know, can I get my program to know to do what you meant?
Right.
No.
So I guess my curiosity is more about, you know, knowing what you know, what percentage of programs support contracts support.
Oh, I see. Well, if we restrict ourselves to contracts that, you know, have a nice semantics in the sense that what the solidity code does and what the byte codes do are reconciled. All of those should port over directly, right? Now, if the solidity code doesn't do what the programmer wants, it's still not going to do what the programmer wants.
So we need to prepare to wrap up, and so it's been awesome, your questions, and I look forward to the future of these events. Please join Slack as the primary way to engage. Thank you.
Thanks, Christian.
Yeah. Peace. Thanks, guys.
That was awesome, dude.